All right, so it is 3:30. We can go ahead and get started. Um, so yeah, just to talk a little bit about some housekeeping items. So like I mentioned, probably by Monday, I would like to release at least part of the specifications for your final project. Now, I think usually what prevents me from releasing the specifications earlier rather than later is the amount of time that it takes to scope out, new and interesting backup data sets. So I usually supply three backup data sets that you can use in your project, just in case you don't want to, work on your own data set that you found yourself. So either option is totally fine. So yeah, stay tuned for more information about that. Um, and yeah, a couple of other things. So our next homework assignment is due on Friday. And I wanted to talk a little bit about just the rest of the checking Tuesdays that you might expect. So, some of you at this point have had your two checks. So yeah, so the bullet point is everybody in the class will be checked exactly 2 times. The final check will be the Tuesday after you've submitted your 12th homework assignment. Now, if it's the case that, for instance, maybe you didn't submit that 12th homework assignment because you've kind of reached your drop the two lowest and you feel good about where you are in the class, then we will still check you, but it will be on the most recently submitted assignment that you did in fact submit. So basically, you will be checked, exactly twice. So yeah, do you know be on the lookout for those emails up until that date. And then soon I would also like to post, maybe within the next few weeks, I'd like to post a practice test for the final exam. So just as a reminder, the final exam will be on the last day of class. It will be in person. And as I mentioned, at the beginning of the semester, everybody that would have had a conflict with the in-person nature of that exam should have reached out to me at that point. So I'm assuming that unless you reached out to me at the beginning of the semester, you're not going to have a conflict with taking that exam, and that will be in person. Also, bullet point. So even though this is an online class, and I'm currently living in California, I do come to Champaign at the end of every semester while I'm doing this online teaching thing. So I will be able to see you guys in person. I will be proctoring that exam myself. And then the final project, essentially what that is going to entail, it's going to be comprised of three main components. So you'll write up with your group a report. And that report will be in the form of a Jupyter notebook. So that's going to be the main component of your project. That'll be the bulk of the points. But also during the 3-hour period in which we have our class final exam scheduled, we'll actually be presenting those presentations live in person. Now, again, at the beginning of the semester, I mentioned, if you know that you would be unavailable during that time, you should have reached out to me and we, would have discussed some backup plans. So I'm assuming that unless you reached out to me at the beginning of the semester, you will be available for those in-person presentations. So I will also be physically present at those in-person presentations. So yeah, I'm looking forward to seeing what you guys have learned or will have learned in the class and kind of seeing how you put it all together towards, exploring data sets that you hopefully find interesting. And then the final part of that project will be peer evaluation. So unless you're in the top ranked, or well, I'll say this. So generally speaking, the peer evaluation part will come in two components. So you will be randomly assigned another group to watch their presentation, and then you're going to give peer feedback to that group. And then you're also going to be randomly assigned to read another group's report, and you'll also give feedback to that group's report as well. So the due date for the final project will be on the day of those presentations, and you can find that on the syllabus or the course schedule. I don't know what that date is off the top of my head. Let's see, that is Wednesday, May 8th, 8 to 11 a.m. Okay, cool. And I will have I'll book a room for that location at that time. And then someone's asking, will the presentation format be business professional? I mean, not really. I mean, it's just a class presentation. I mean, you can dress up if you'd like to or something, but this is relatively informal. You can think of this, the target audience for your reports as well as your presentation would theoretically be a student in this class, or someone who has the same level of knowledge about these unsupervised learning techniques as you. So it's, with regards to dress code, I guess you could say it's pretty informal. That's a good question. And then just to confirm, the final exam is during our class time that Tuesday. Yeah, so that'll be on the last day of class, Tuesday, April 30th, 3:30 to to 4:50. Okay. All right, cool. So yeah, so be on the lookout for content that I will be posting. But yeah, any questions on any of the housekeeping elements before we dig in? Okay, so what we're going to do today is we're going to talk a little bit more about the non-negative matrix factorization. So what we discussed on Tuesday's lecture was, one second here. What we discussed in Tuesday's lecture was the wide variety of interpretations that you can end up extracting from our W and H matrices, which we are calculating in the non-negative matrix factorization. Bear with me for 1 second here. I'm just going to set up the PDF. So we talked about how we can go about interpreting those W and H matrices. But what we actually did not get to is, how we actually go about finding those optimal W and H matrices. So what we discussed, bear with me here for 1 second, was that the non-negative matrix factorization technically comes from an optimization problem, right? In which we are trying to find the optimal W and H matrices, which we are constraining to be non-negative, that minimize what we call the reconstruction error. So ideally, we'd like to select the optimal W and H matrices such that when they multiply, they roughly are going to give you the same initial X matrix, which you are trying to cluster, if you will. So this is a optimization problem in which there is no known polynomial time algorithm which will find the global minimum solution. So what we do instead is we use a carefully constructed version of a gradient descent algorithm. So like we mentioned, these update equations for our W and H matrices, they don't look like the normal gradient descent equations that we usually use in the gradient descent algorithm. And the reason why is basically what we were deriving here. So essentially what we're doing here, or what we were working on was how to derive the optimal, or basically how to come up with a set of carefully selected update equations such that our main constraint of the optimization problem, i.e. these matrices are non-negative, such that this main constraint is met, essentially. So, when we construct these update equations, we want to enforce, so basically we want to make it such that all resulting W and H matrices never become negative. So part of the way that we do this is we first randomly initialize our W and H matrices with non-negative values, but then we're carefully selecting these updated equations such that W and H never become negative. So here's how we go about enforcing that, essentially. So what we do, and this is what we do with all gradient descent algorithms, we take or calculate the gradient of our objective function with respect to the decision variables that we are trying to find the optimal solutions for. So that would be our H and W matrices. So what we were doing first, right, is we calculated the gradient of our objective function with respect to H first, and then we set up our, more basic gradient descent update equation for H such that we would like to move in a certain step size in the direction vector that decreases F the fastest. So that's basically going to be the negative gradient of F. And so we were asking ourselves, well, okay, how can we carefully select this step size matrix, i.e. this matrix of step sizes, to ensure that every new H is always going to be non-negative? So here's what that matrix of step sizes is stipulated to be. So the researchers that created the non-negative matrix factorization carefully selected this following matrix here. Now, typically, right, when we're dealing with matrices, we don't actually use the division symbol, right? The equivalent, if you will, of the division symbol is taking the inverse of that matrix. So this, operator here, this is actually not the inverse. So actually, what this division symbol here represents is basically going to be the Hadamard division, or in other words, it's going to be element-wise matrix division. So you simply just take the first row and column of H, or of the H matrix, and divide it by the first row and column of this matrix, so on and so forth. And basically, this is the division equivalent of the Hadamard product, which is, element-wise matrix multiplication. So let's see how this carefully selected alpha matrix is going to help us achieve our overall goal here of never getting a negative H. So we plug in this carefully selected alpha matrix into our update equation for H. Okay, and then the whole point of this carefully selected alpha matrix is we're going to get some nice cancellations here. So basically, because this is simply just an element-wise product, we can actually just distribute this alpha matrix here to these two terms here. And so we end up getting this update equation here. Okay, now take note, we also end up seeing, so we have this element-wise division going on here. So basically, this is what this product, element-wise product, gives us here. Okay, and so let's focus on what this piece, or what this matrix would look like. So what do we think this matrix would look like? So again, we're basically, for instance, taking the first row and column of this matrix and simply just dividing it by the first row and column of this matrix. And these two matrices are the same. So therefore, right, we're simply just taking an observation. Well, now, okay, so it's actually not going to be the identity. So I can see where you might come up with that. But it's actually simply just every single observation in these two matrices, which are the same, are simply just, dividing each other. Yeah, exactly. So it's actually going to be a matrix that is comprised of all ones. So what this element-wise product will give us is, so therefore, what is this matrix going to be? So we're basically conducting element-wise multiplication of the H matrix times, yeah, exactly, times a matrix comprised of all ones. So this product is simply just going to be H. So what we end up getting here is an H here and an H here, which we're subtracting. So therefore, the cool or useful aspect of this carefully selected update equation is that these terms, the first term and the third term, cancel each other out. So now what we are left with in our update equation is simply just this term here, okay? And given that we are now just left with this term here, I can now, in fact, guarantee that no matter what I do, this value or this matrix is always going to be non-negative, right? Because basically what I'm doing is I'm stipulating that, number one, my X matrix is always, it has to be non-negative in order for NMF to work. And then furthermore, I'm randomly initializing my W matrix and my H matrix to be non-negative. So therefore, this entire product or division of matrices is always, there's no way for it to become negative, right? Because if you're performing matrix multiplication of two non-negative matrices, well, that matrix multiplication there's no way for it to become negative. And similarly, if you're performing element-wise division or multiplication of two non-negative matrices, there's nothing that you can do to make that resulting matrix non-negative. So therefore, for any given H, we get in any one of these update equations, the H is never going to become non-negative. So therefore, what we're doing in this heuristic algorithm is we are moving in a direction that minimizes F, that also simultaneously keeps H always non-negative. Okay. Questions on that? Okay, so basically that derives our update equation for H. And so our update equation for F is going to follow a similar pattern. So again, I'm going to take the gradient of our objective function F, this time with respect to our W matrix. Okay. And again, there's, it's a little bit out of scope calculating the gradient of matrix multiplication, or basically calculating the gradient of matrices. But essentially, when we calculate that gradient of F with respect to W, this is what we end up getting. And so again, what this direction vector represents is the direction that moves, or that, increases F the fastest. So what we would like to do, because we're trying to minimize F, is we would rather like to move in the direction that decreases F the fastest. So what we're going to do instead is we're going to move in the negative gradient direction with respect to W. Okay. So we're going to plug in this negative gradient into our typical update equation. So basically that negative gradient is what we end up getting here and here. Okay. And so furthermore, just like we saw with the gradient equation, or the update equation for W, we would like to move in that negative gradient direction, but only so far such that our resulting W never becomes negative. So therefore, we need to be careful about how we select this new matrix of step sizes we call beta. Okay. So the researchers that came up with the non-negative matrix factorization stipulated that matrix of step sizes beta should be the following, where again, we are performing element-wise division of the two matrices here. And to see why this works, why do we select this particular beta matrix? Well, we can see that if we take our update equation and we plug in that carefully selected step size beta matrix, then what we can do is we can take this beta matrix and distribute it to the two terms in the negative gradient with respect to W. Okay, and the whole point of this is to get some nice cancellation. So when we distribute that beta matrix, we're going to get one of these terms here, which, like we saw in the previous update equation, is going to give us simply just a matrix comprised of all ones, which means that this value here is going to be simply just W. So therefore, we end up getting some nice cancellation. So W minus W. Okay, and so what we are left with in this update equation, simply just this term here, which is guaranteed to always be non-negative. Because again, if X is stipulated to be non-negative and the previous, W and H matrices are, non-negative, however it is that they're formed, then there's no way for any of these matrix multiplications as well as element-wise multiplications and divisions, there's no way for this expression here to become negative. So therefore, in this update equation, we are always going to be moving in the direction that decreases f the fastest, while only moving so far such that the W matrix always remains non-negative. Okay, so this is where our two carefully selected update equations come from in this heuristic algorithm. Okay. Yeah, so basically this is the derivation of the non-negative matrix factorization heuristic algorithm. Any questions on that? So I wanted to talk about one more thing before we move on to the application. So I ideally like to get through all this Unit 12 content today, but it's probably not going to happen. So I think what I'll do is I'll talk about one extension, I guess you could say, or another version of the non-negative matrix factorization problem, and then we'll move on to the MNIST application. So the the non-negative matrix factorization version, I guess you could say, that we've been talking about so far, could be classified as a purely unsupervised learning analysis, because our assumption was, previously, that this X matrix, which we were decomposing into W and H, our assumption about that X matrix was that this is a complete matrix, or in other words, there are no missing values in X. So in the case of our Netflix, like an actual Netflix data set, where for instance, the rows of X represent the users and the columns of X represent the movies. Realistically speaking, there's going to be no user who has seen all movies. So inevitably in this X matrix, you're going to get, at least one missing value for every row. So, the question is, how does that play in to our, non-negative matrix factorization optimization problem that we're solving for? Well, the nice thing is we actually more or less end up using the same optimization problem, but we're just going to slightly modify the actual values that we're calculating the error for. So if it is the case that we have some sort of a X matrix that has a series of missing values. So let's just say here, here, and here, for instance. The only thing that we need to do to update this non-negative matrix factorization is to construct a 0, 1, for instance, weight matrix. We could call that T, where if there is a corresponding missing value in X, then we put a 0 in that weight matrix. Alternatively, if we know the corresponding value in X, then we put a 1. Okay. Now you can actually extend this technique if you'd like. So for instance, this technique that we're describing here is it's an extension of the non-negative matrix factorization. So we call it the WNMF, i.e. the weighted non-negative matrix factorization. And so technically, you don't actually have to use 1 for the observations in the X data set that are not missing. You could use any non-negative, or excuse me, non-zero value that you might want. So for instance, if you want your non-negative matrix factorization to focus more strongly, if you will, on ensuring that the error, let's just say for this particular term, is not high, then you might decide to, use a higher weight for this corresponding value in the T matrix. So that's an extension that you could consider based on, your research goals. Like if you wanted some error terms in this W times H matrix to be considered more strongly, then you can, increase that corresponding weight. But the main issue that we're focusing on here is what to do in this optimization problem if your corresponding value in X is missing. So we simply just take that weight matrix T, and then we perform element-wise, or the Hadamard product multiplication to the original difference that we were calculating here. So essentially what that does is, or what that equates to is basically saying, we'd only like to consider the error of the terms in this difference that actually have a corresponding value. So in other words, what that means is that we're only going to add and square the error that we would see for the difference between this term and this term. So the difference or the error that would have existed between this term and this term is simply just not going to be considered. So for all intents and purposes, what this objective function is indicating is we only consider the squared error for terms in X that values in X that do not have missing, or that are not missing. Okay, so all this really equates to is simply just focusing on fewer terms in the objective function. But then after that, everything else about this non-negative matrix factorization is going to be the same. So we're still looking to select the optimal non-negative W and H matrices that minimize the non-missing terms in this corresponding difference here. Okay. And so similarly, the way that we would interpret our W and H matrix would be the same. So for instance, our W matrix represents a lower dimensional representation of the rows, in our case, users, but it also represents a clustering, a fuzzy clustering of the X rows i.e. users in our case. And then similarly, we still get the same interpretation of H, where H represents a lower dimensional representation of the X columns. So for instance, the movies. And it also represents a fuzzy clustering of the X columns. Okay, so our interpretation of the W and H matrices is the same. However, in this case, in which we have missing values in X, we actually we get this added bonus in that not only are we performing unsupervised learning analyses, i.e. not only are we finding this W and H matrices that we can use to learn more about this X matrix, but in addition, we can use these W and H matrices to perform supervised learning. Or in other words, we can multiply these W and H matrices together to give us predicted values for all of the missing values in X. So WH gives us predictions for the missing values in X. So therefore, one of the many uses that non-negative matrix factorization provides is for the application known as collaborative filtering or recommender models. So the recommendations come based on the identified clustering structure of the rows and columns. And then we basically use that clustering structure to make recommendations. So for instance, we can use that to recommend or, predict, what kind of rating, this user would give for this particular movie based on, other movies that they have liked, as well as other movies that other people have liked. And so we do that simply just by multiplying W and H together. Okay. All right, so cool stuff. Any questions on that? Okay, so I'm going to come back to the benefits and drawbacks of non-negative matrix factorization and weighted non-negative matrix factorization probably on Tuesday. And in addition, we're also going to talk about some other ways to go about modifying the non-negative matrix factorization optimization to achieve other goals, such as, giving you W and H matrices that are more interpretable. But I think we probably won't have time for that today. So in order to create a more interesting homework assignment, we'll switch gears for now. We'll focus on performing a non-negative matrix factorization on the MNIST data set. Okay, so our MNIST data set, if we recall, we've seen this a lot of times, is comprised of 1,797 images on the rows, and each image has 64 pixels or 64 columns in X. So what we're going to do, so we'll start with a dimension of 10, so R equals 10. What we're going to do is we're going to solve for the optimal W and H matrices such that when they multiply together, they will approximately reconstruct this original XMNIST data set. And ideally, what we will be able to do with these W and H matrices is make some of the following interpretations. So number one, with this W matrix, we can create, in our case, 10 image clusters, right? Fuzzy clustering membership matrix for each of the images. So for instance, we can use, let's just say, the first row in this W matrix to create a probability distribution, basically, that indicates the extent to which this particular image belongs to image clusters 0 through 9. And then furthermore, if we wanted to learn more about, for instance, what pixels or what pixel relationships characterize the observations that have high cluster 0 membership scores, we can examine the corresponding row in our H matrix. So that's something that we're going to do. And then furthermore, so basically, we examine the W matrix to cluster the rows, or in our case, the images. However, as we've discussed, non-negative matrix factorization also allows for us to cluster the columns. So in our case, we can examine our H matrix to give us a fuzzy clustering of each of the 64 pixels. So for instance, this would be fuzzy cluster, or this would be pixel cluster 0, this would be pixel cluster 1, so on and so forth. And so, for instance, if we wanted to learn more about, let's just say, pixel cluster 0, for instance, what type of images characterize pixel cluster 0, then we can take a look at its corresponding column in the W matrix. So basically, based on the weights that we see here, we're going to see that some images have or characterize this, the pixels that correspond, or the pixels that have high cluster 0 membership weights. Okay, and so furthermore, this W matrix also, maybe we don't want to use this as a clustering algorithm itself. Maybe we simply just want to use W as a lower dimensional representation of our images in X. So that's something that we can also do. And then furthermore, maybe we don't want to cluster the 64 pixels in H. Maybe we'd rather use H as simply just a 10-dimensional representation of each of our pixels in X. So these are all things that we're going to explore to learn a little bit more about, what are the essential, number one, like, is there a clustering structure in X when it comes to the images as well as the pixels? But then also we're going to explore, for instance, so we're going to focus a little bit more on clustering and representing the images because, as we're going to see, this is going to provide more useful insights. So essentially what we're going to see here is, or, what we're going to explore is, are there particular pixel relationships, or basically image profiles, you can think of them as, are there particular image profiles or, pixel pieces, I'll call it that, such that they are the most useful when it comes to reconstructing the original images in the data set? So these are all things that we're going to explore. So, so we have our MNIST-X data set. We are going to scale that data set again, simply just by dividing by 255. And again, it's generally speaking not a good idea to z-score scale an image data set. But in particular, it's going to be non-usable if we're to z-score scale our MNIST data set, because if we're z-score scaling, right, we're going to get negative values in X. So that's not going to work for our non-negative matrix factorization. So if you plan to scale a given X data set before plugging it into NMF, you want to make sure that you're using a scaling technique that does not force any of the values to become negative. So that's something to consider. Now, first, what we'd like to do is we'd like to focus on clustering the images or the rows of X. So what we might decide to do first is create a set of TS&E plots that identify the clustering structure of the images in X. So we've seen this code before. And given that we want to focus on the clustering structure of the rows, i.e. the images, we're not going to transpose X. We're simply just going to plug in X, by itself into the TS&E function. Because generally speaking, all of the algorithms that we're discussing here, except for fuzzy C-means, assume that the rows are the objects that you'd like to cluster here. So we're, this is old hat here. We're simply just using the TS&E algorithm. So we've plugged in the MNIST data set before into a TS&E plot, and we did in fact find evidence of a very strong clustering structure that has quite a lot of association with what the digits are, or what the images are actually a picture of. But we do see that, for instance, there is some overlap between some of the TSNE identified clusters here. And furthermore, we see that some of the images actually split up into multiple clusters, if you will. So we've seen all this before. However, like we discussed, we're also going to focus on clustering the pixels as well. So if we'd like to use the TSNE's definition, if you will, as to what makes a clustering structure, we can also, basically identify or look for any clustering structure that might exist in our 64 pixels. So to examine that, what we're going to want to do is we're going to want to, take our X matrix and transpose it such that now our pixels are in the rows and our 1,797 images are in the columns. And so therefore, we want to identify any existing clustering structure in pixels. We simply just use the TSNE algorithm with the transposed X matrix. And so let's see if we see anything here. Okay, so the evidence for a clustering structure in the pixels, it's definitely not as strong. Maybe we see some evidence of maybe 2 pixel clusters here. And again, because there's only 64 observations in this data set, you're going to want to not focus a whole lot on some of the higher perplexity values. So for instance, we see this here with a perplexity value of 50, right? What we're assuming in the TSNE algorithm is that every observation in this data set has 50 nearby neighbors. So in a TSNE plot that looks like this, because we're forcing 50 observations to be close to any given one point, the existing separation that we kind of saw in some of these lower perplexity TSNE plots is going away. So bullet point, I see maybe some evidence of a slight clustering structure with 2 clusters in the pixels. However, what we want to remember is all of these clustering algorithms, as well as clustering related algorithms like the TSNE algorithm, all of these algorithms are actually going to rely on a different definition of a cluster, basically. So essentially what we're going to see is that the clustering structure detected by non-negative matrix factorization is actually going to have a strong amount of disagreement with what we see in the TSNE plot. But that doesn't necessarily mean that what we're detecting in the non-negative matrix factorization is non-meaningful, but more so we're detecting a different type or a different definition of clusters. So, we wanted to kind of compare these different clusters with 2 different techniques to kind of compare and contrast the differences here. So, okay, so I've been doing a lot of talking. Any questions before I move on? Okay, so first let's focus on clustering and representing the images in our X matrix first. So representing them with a lower dimensional representation. So as with many of these other clustering algorithms where there's some sort of parameter that we need to tune, we want to think carefully about how we might select the parameter that we need to pre-select ahead of time. So for the basic non-negative matrix factorization, there's only one parameter that you need to think about, i.e. what is your R value? So how many columns do you want in your W matrix and how many rows do you want in your H matrix? So that number is the same. So one way, or one common way that we've determined, or we've essentially used to determine what might be a good parameter value, is we've created alpha plots. So we could construct a NMF alpha plot to give us some insights about is there a particular cluster number K or R in our particular case, such that we hit this point of diminishing returns with respect to the function, i.e. the objective function that we're trying to minimize. So we can construct that NMF elbow plot in the following way. And this looks very similar to what we've done in the past. So for instance, I can iterate through a series of K or R values. And I'm going to use my NMF function where I stipulate the number of components or the number of columns in W and rows in H. Now, again, you want to remember that the non-negative matrix factorization heuristic algorithm is non-deterministic because we randomly initialize those W and H matrices. So generally speaking, you should stipulate a random state. So when using the NMF function, I first instantiate that NMF object. And then when I'm ready, I fit it with my X matrix, so not transposing it. And if I want to extract the objective function or the optimal objective function value for my W and H matrices that were solved for, i.e., if I want to extract this value, i.e., the thing that we're trying to minimize, then I can use that reconstruction error parameter. Okay, so I simply just plot the corresponding reconstruction error on my y-axis for each of my cluster numbers, or my R values that I tried out in the non-negative matrix factorization. And so, unfortunately, I'm not really seeing any strong evidence of a elbow here. It's, much more of a gradual decline. But, if I were to, try to find, a couple points where we start to see somewhat of a leveling off, I might say that, for instance, like something's leveling. We start to see some leveling off at, K equals 5, K equals 10, maybe. So I'm definitely going to try out, I'm going to start with more of a naive implementation. I'm going to start by using K equals 10 clusters, but I'm also going to try out other W and H matrices. So one of these, one of these is going to use R equals 5. Another one is going to use R equals 20. And I'm going to explore some of the other potential goals that I might want to pursue in a non-negative matrix factorization to help me choose, what might be the best R to use. But for now, let's just explore what a R value of 10 will give us. So with that in mind, I'm going to use that non-negative matrix factorization function again. Okay, I might need to reboot here for a second. Okay. So there we are. So use that NMF function again. NMF is from scikit-learn, so that's good. I'm going to stipulate that I'd like 10 components, or I would like to stipulate my R value to be 10. I'm going to set a random state. I've instantiated that NMF object. And if I'd like to both basically run the NMF heuristic algorithm as well as simultaneously spit out a relevant output, as I've seen with other scikit-learn clustering functions, I can use fit transform on X. And so what that fit transform function will return is it will give me the W matrix. If I want to get the H matrix, then I can use the components attributes or attribute. Okay, so the first thing that I'd like to do is explore that W matrix. So I'll put that in a data frame. Okay, and so that W matrix, as I would be expecting, is going to have 1,797 rows and 10 columns. And again, each of these columns represents or could represent a image cluster. So basically, this W matrix by itself it's almost a fuzzy clustering membership matrix. But like we've seen, the values in any one particular row are not necessarily going to add to one, or in other words, not look like a probability distribution. So we can see that here. So if we wanted to actually, get that W matrix to look like a fuzzy clustering membership matrix, we can, use the simple transformation that we talked about on Tuesday, where we simply just divide each observation in a given row by the row sum, and that will basically force each row to look like a probability distribution. So we're going to do that in just a second. However, if I wanted to, before transforming W, if I wanted to visualize, use a useful visual aid for, visualizing each of these 10 columns in W, then I could use my TS&E plot, and this could be useful. So we've created these, we've used TS&E plots like this before when we were performing fuzzy cluster, or when we were performing fuzzy C-means. However, so we've used this code before, but I want to make one amendment. So there's a slight difference between the code that we're using here for NMF versus the code that we were using for fuzzy C-means. The only difference is here, we're not going to stipulate that V min is 0 and V max is 1, like we did with fuzzy C-means. Okay, and the reason why is basically in this untransformed W matrix, we already know that these values don't necessarily add up to 1. So therefore, we shouldn't necessarily, force the values that we're looking at here in the color bar to be between 0 and 1, because it's actually, technically possible for some of these values to actually be greater than 1. So basically, we'd be missing out on, insightful visualization. So we're simply just going to not, set that color bar to be between any particular range. So, actually, we can see here that this particular color bar, which visualizes the first column in W, we can actually see that these values, range between 0 and like 0.1. Okay, so we can visualize or color code our TS&E plot by, each of the corresponding columns in W. That's annoying. Bear with me for seconds. And we can use this to learn a little bit more about our clustering structure. So number one, take note, right? The cluster, the weights, basically these W columns, actually do not seem to have a very strong association with the clustering structure identified by the TS&E algorithm. So for instance, the TS&E algorithm, identified these 3 sets of observations as distinct clusters. But, if we look at the column W, or this particular column in W here, we can see that those values that have high weights for this column actually end up being those that exist in all 3 of these clusters here. So we're not seeing that strong association. So that begs the question, is what we're identifying here in W, are we actually, extracting meaningful insights because we don't have agreement or any agreement or a lot of agreement with the TS&E plot? So not necessarily. So let's actually explore some of these clusters here. So let's take a look at the observations that show up in this set of points here in the TS&E plot. So if we identify the columns of W that have high values for those corresponding observations, so you can see that it's going to be high column 2 values, high column 8 values, and to some extent high column 9 values. So that's this here, and this here. Basically, the 0 images are going to have high W values for these 3 columns in particular. Okay, and also, take note that the first image in the data set is in fact a 0, and so we actually end up seeing that here. So this first image does in fact have some of the highest values for these 3 W columns. And so you want to remember the way that we would actually go about reconstructing the first row in X which we know actually represents a 0, would be multiplying this row in W by all of the rows in H. Okay? And so each of these rows in H actually represents a pixel profile. I'm so sorry. I need to step away for 1 second. My dog is having a little bit of an emergency. I will be back in 10 seconds. Okay, sorry about that. My dog is a little bit sick right now, so I just wanted to attend to that. Okay, so yeah, so basically, to get this first row in X, which is an image of a 0, we're going to multiply this first row in W by each of the rows in H. Or in other words, we are creating a linear combination of the 10 rows in H, where the coefficient in, multiplied by each of these rows is these corresponding values in W. So for all intents and purposes, for the most part, what we are doing is we are, because the weights for these particular pixel profiles are so high, or comparatively much higher, for all intents and purposes, we're adding up simply just these 3 rows together. Okay? And so we can see that a lot of these other W values are very small, if not 0. So basically, if we wanted to reconstruct the first row in X, it would basically be this linear combination here, 0.07, 0.02, blah, 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 blah. This is a little sloppy, so my apologies. And so we can actually visualize, so each of these rows in H is actually 64-dimensional, which represents a pixel relationship. So we can actually visualize each of these rows in H as follows. So basically, what we're saying here is that to reconstruct as best as we can the first row in X, then for the most part, what we're doing here is we are combining this pixel piece, and this pixel piece. So let's see what we get when we combine these pieces. So we get something that looks like this, something that looks like this, and then something that looks like this. All right, so that looks like a 0 to me. So it makes sense. I would guess, I would assume that, basically, if I was to actually multiply this row of W times all of the rows in H, that I would end up getting a pretty good reconstruction of the actual image in X, or actual first row in X, which looks like a 0. Now, what I'm going to see is I unfortunately will not be able to say the same thing about some of these other digits. So, what we're going to see here is that by simply just using 10 rows in H, I haven't quite given myself enough fine-grained of a set of pixel pieces to faithfully reconstruct all types of images in this data set. So we're going to see that here in a second. Okay. Yeah, any questions on that? Okay. So let's actually see what kind of reconstruction that we get. Now, before we do that, we would like to, so basically, the reconstruction that we had done here, this is with our basic, our non-transformed W matrix. So we haven't actually row scaled the observations yet. And so therefore, this W matrix by itself is simply just a 10-dimensional representation of our images in X. But if we wanted to actually force that W matrix to look like a fuzzy clustering membership matrix, then that is something that we could do. So we could take our original W matrix, and then we can divide each observation by its row sum. So we can do that by dividing by NP, the NP sum of W, and then stipulating these parameters here. So basically this enacts that row sum scaling, if you will. And so we end up getting this transformed W matrix, where now we can see that each of these rows will actually sum to 1. And because each of those because that W matrix was non-negative, this allows for this row sum scaling to actually give us a set of rows that are in fact a probability distribution, therefore making a interpretable fuzzy clustering membership matrix. Okay. Any questions on that? So, given that I'm actually technically now representing this W matrix as a fuzzy clustering matrix, I might be curious to see, what kind of relationship do I end up getting, or what kind of association exists between this fuzzy clustering membership matrix W and my TSNE plot. So I'm going to color code my TSNE plot by each of the columns in my transformed W matrix. And this is the exact same code that I saw before, but now, again, there's one stipulation in that I'm now stipulating that the min and the max of the color bar should now, in fact, be set to be between 0 and 1. And this is because I'm assuming that, we're not assuming, this is because it is the case that all of my values in my transformed W matrix will in fact be between 0 and 1. So in other words, I'd like to represent each of the corresponding values as being a probability and a probability distribution. Okay. So unfortunately, or not necessarily unfortunately, I also in fact see that there's not this strong association between the clustering structure that the W matrix picked up and the clustering structure that the TSNE matrix picked up. If I did see a strong clustering structure, for instance, I would see very high, cluster weights, for the set of so very high cluster weights for one and only one cluster for these observations here. But that's, not something that we're seeing. So we are seeing some higher cluster weights for actually 3 clusters for all of the observations here that showed up in this TSNE plot suggested cluster. However, as we've seen, just because a given clustering algorithm doesn't agree with what the TSNE plot says does not mean that there's no meaningful insight. So in fact, we did, in fact, pick up on some interesting insights, which was telling us that the most important pixel pieces, or the most important 10 pixel pieces that optimally reconstruct the X matrix are going to be these pieces here. So these are going to be some of the most important pieces for, minimizing the total amount of reconstruction error. Okay. So you might find that useful. So let's see a couple other things. So for instance, if I wanted to, for instance, extract that cluster membership score for a given, let's just say the first observation in the data set, I can use the iloc function. Simply just looking at the first row in that transform W matrix. And so I might interpret that, for instance, as saying that the first image in the data set, 28% belongs to cluster 2, 10% belongs to cluster 3, so on and so forth. And so I'm identifying these 10 clusters. And then I asked myself, like, well, what pixel relationships, characterize each of these 10 clusters? And so again, each of the 10 clusters identified in W maps on to the attribute or pixel relationship identified in the 10 rows of H. So this is how we would actually, visualize each of those 10 rows of H. Okay. And so let's actually check how well our reconstruction was by, multiplying W times H. So this is our actual first image in the data set. So we do see that it is a 0. And so let's actually see, what kind of image would we get if we actually multiplied the first row of W times all of the rows of H. So we conjectured that we would get a pretty good reconstruction. So let's actually check that. So I'm going to take the dot product of that first row of H and all of the rows of H to get this reconstructed first row of X. So I'll call that Y0. Okay. All right, cool. So this is what my reconstructed first image in the data set looks like. And if we compare that to my original first image in the data set, well, that looks pretty good, right? But all things considered, we might expect for the zeros to look pretty well reconstructed because we can see that, we have a lot of the important pieces of a zero. So we have the bottom and the top half, we have the part on the left, we have the part on the right. So it's pretty easy, to see that a 0 would be well reconstructed. But we might want to ask ourselves, do we have all the pieces that we need to reconstruct like a 2 or a 3? So let's find out. So what we're going to do now is we're simply just going to multiply the entire W matrix times H. Or in other words, we're going to multiply each of my rows in W times each of my rows in H. And so therefore, my corresponding Y matrix is going to be my reconstructed version of X. So let's visualize for comparison purposes some of the the first 3. So for each of the digits in my X data set, let's look at the actual image of those data sets, and let's look at the reconstructed image of, or reconstructed version of those images. Cool. So I can see that a lot of my zeros end up looking pretty good. So they're pretty well reconstructed. But then, as I move on to the 1 images, it's starting to look a little fuzzy, right? If I move on to those 2 images, not looking very good. So pretty, not crisp at all. The 3s, the 4s, yeah, the 4s are really bad. So, and we can see that, the 4s, it just doesn't really look like we have enough nuanced pieces to faithfully reconstruct a 4 here from these rows of H. So it makes sense that, the 4s were unable to be faithfully reconstructed here. So given that, so for instance, if our overall goal of this analysis was to faithfully reconstruct the images of X, or the images in my X data set, what might I do? So would I want to decrease the number of rows in H, or would I want to increase the number of rows in H? Yeah, increase. Yes, I want to give myself, more of an opportunity to create more flexible, nuanced pixel pieces, if you will, to create a better reconstruction. So I'll explore upping that R value in just a second. But yes, I'm seeing a question here. So it says, does it mean that when we reconstruct, there must be some images that will not restore the important elements well? Yeah, so that's what we're seeing here. So we are seeing that the 0 images were pretty well reconstructed, but some types of images were not as well reconstructed. So yeah, so it's yeah, so for the most part, so ideally, all of the images will be reconstructed pretty well. However, inevitably, some images, depending on some sort of characteristic, will have better or worse reconstructions. Okay. So for instance, we might want to learn a little bit more about, for each of the digits in our data set, what rows of H are considered to be the most important. And the way that we learn about what rows of H are the most important in the reconstruction is we look at, how high are the corresponding W values, right? So we can see that for the 0 digits in my data set tended to have very high W values for image, for like this row here, this column here, and this column here. And that corresponds to this row of H, this row of H, and this row of H. So that makes sense. So these, 3 pixel pieces do in fact, add together to create a pretty well reconstructed 0. And so we can also see that, there's just a few pieces or just a few W column values that are high. The other W column values are comparatively a lot lower. However, if we were to move on to, let's look at another one here. Look at 8. Now 8 is quite different, right? So we can see that our reconstructed 8 images kind of just look like a big blob of points. And, to be honest, that makes sense here. We didn't really give ourselves enough nuanced pixel pieces to reconstruct these little holes in the 8 images. And furthermore, we can see that actually a lot of the corresponding W values are set to be quite high for 8 images. And so for all intents and purposes, we're saying that, the way that we're reconstructing an 8 images is we're simply just taking all of these pixel pieces and we're just mashing them together. So that kind of explains, why we end up seeing an image, like a very undefined image here that does in fact look like we've just kind of smashed all of these pixel pieces together, if you will. Okay, a couple of other things. What do I want to say about that? Okay, so I'm actually working on a project right now in which the TS&E algorithm has failed me. And the reason why the TS&E algorithm has failed me is because I was trying to input a TF-IDF matrix into it, or in other words, a document term matrix, where basically the row that I'm trying to cluster is a text, basically. And the columns are the words in that text. So basically, there's a non-zero value if that word exists in the text, and it's a 0 value otherwise. So the bullet point here is that my X matrix in my project that I'm working on, it's going to be very sparse, right? It's going to have a ton of columns. So basically all words that exist in all texts. So it's going to have a really high dimension, and it's going to have a lot of zeros as well. So unfortunately, the TSNE algorithm by itself is going to fail me in scenarios such as that. So the TSNE algorithm is not that great when you have very high dimensional data sets and you have a lot of sparsity. It kind of just spits out this unintelligible blob, which basically tells you nothing. So what I decided to do instead was use the non-negative matrix factorization to represent my high dimensional X data set with a much lower dimensional W matrix. And then what I did is I plugged that W matrix into the TSNE algorithm. And I was actually, in fact, able to see a clustering structure in that W matrix. So if you're, in fact, choosing to use the non-negative matrix factorization as a dimensionality reduction algorithm, then that can basically be a workaround if you have these super high dimensional data sets that end up causing problems in your clustering algorithm. So for instance, if it's taking up too much computational resources because your X matrix is too large, it has too many attributes, or if the too many attributes in your data set have some sort of property that doesn't really yield insightful results, one workaround that you can, in fact, use is you can represent that high dimensional X with your lower dimensional W, okay? And that is something that we technically could do with PCA as well, right? So we have this high dimensional data set. We could project it onto a certain number of principal components, and we could choose to cluster the principal components, okay? But the problem is we want to remember what are our dimensionality reduction algorithms trying to preserve. So the key thing that you want to remember is PCA is not inherently designed to preserve the clustering structure. So if you decide to cluster the principal components, what might end up happening, it doesn't always happen, but what might happen is perhaps your clustering structure might in fact weaken because we're not trying to preserve the clustering structure. So let's actually see, and essentially what we end up seeing in, when we use the W matrix as a representation of X is that our clustering structure is in fact pretty well preserved. So let's actually test that here. So here's my W matrix. It has 10 columns. So if I look at my pair plot, I'm not really seeing any strong clustering structure by itself, but let me do this. So let me take my original non-scaled W matrix and plug that into my TSNE algorithm. Let's see what kind of clustering structure I get. Okay, cool. So it looks like that I actually did not even need to use all 64 of my columns in X to relatively faithfully preserve the clustering structure of X. So I can see for the most part that simply just by using 10 columns in W, I was in fact able to keep a lot of that same clustering structure that I had observed in the TSNE algorithm when I had used 64 columns. So now, but do take note though that some of the clustering structure is weakened a little bit here. So we can see that, for instance, this pink and this green cluster have been mashed a little bit closer together. So the clustering structure is weakened, but all things considered, given that we're simply just using 10 dimensions, the preservation of the clustering structures is pretty good, all things considered. So very quickly, what I might decide to do is, if I'm having, so let's just say, for instance, I was having a lot of problems clustering this high dimensional data set X with k-means. So what I might do instead is I might instead choose to cluster the W matrix with k-means. I might have better luck. It might be faster, if you will. So that is something that I can do. So I can cluster my data set with k-means. I'll look for 10 clusters based on the suggestions in my TSNE algorithm. And I'm going to cluster my W matrix. Okay. All right, cool. So here I have my k-means cluster labels. And if I compare them to my digit labels, for instance, or actually if I compare them to, what the TS&E plot is suggesting, I can actually see that there is, this relatively strong association between the clusters identified by the TS&E plot and the clusters identified by k-means. So therefore, what this might suggest is that, yeah, like the distinction that exists between these two, focus on this one instead. The distinction that exists between these two k-means clusters is in fact meaningful. There is some sort of meaningful separation. Okay. Shoot. Okay, I think I've run out of time. All right. Unfortunately, I do think I will need to add like 10 additional minutes of video content after class. So I'll record the additional 10 minutes of content soon. And then I will post that because, yeah, unfortunately, we haven't quite got through everything that we need to in order to make a complete homework assignment. So I will post that later. But yeah, I've gone over time, so I will stop there. So let me stop recording.